I'll continue on today's tutorial. This second part is where we'll start speaking finally about self-supervised methods. So here, therefore, we will be using unsupervised and self-supervised interchangeably. So don't worry in the difference of them in the specific setting of imaging. We generally don't differ across them. So make sure we're on the same page. And in this first part, I'll be speaking about mostly denoising. We'll get to reconstruction later. What do I mean by denoising? I mean that the operator A is the identity, and we just need to remove some noise that could be additive or not. So here it's our epsilon, okay, from some noisy measurement, right? Although this will be for denoising, we'll see that all the methods in this part can be easily extended for anything where the forward operator is invertible. If A is not the identity, but it's invertible, you can easily adapt any of the methods I'll be speaking about, right? Okay, so one thing that it's important to bear in mind when looking at self-supervised learning is what is the oracle? What is the best we can do? And the best we can do is obviously supervised learning, and supervised learning with infinitely many data. And what do we obtain when we do supervised learning with infinitely many data? In the case where we use a squared loss, which is one of the most common losses that people use in practice, is that we'll get the conditional mean, so the expectation of the image given the measurements. So in the Bayesian setup, that would be the posterior mean estimator. So this is the best we can get if we want to minimize the distortion, the L2 error of a reconstruction. Here, I will skip other types of estimators that do not look at giving low distortion images, but giving more good-looking images, which people call perceptual images. I recommend you looking at that paper by Lyon and Michaeli, where they discuss other types of estimators that you can look at. So when we speak about unsupervised or self-supervised learning, the main goal will always be to try to build a loss that is self-supervised, so it only requires Y's, so measurements, and that can approximate the supervised loss. What do I mean by approximate? That it's either proportional or that it shares the same minima. If it shares the same minima, then optimizing the self-supervised loss will be the same as optimizing the supervised loss, right? And if we are optimizing the supervised loss, we know that we'll get the posterior mean, the MMSE estimator, which is the oracle we can get, all right? And for denoising, there is this very easy decomposition that in the literature is called as Efron's optimism theorem, which basically we take the supervised objective and we will separate it in two now. Well, the first term is just measurement consistency, how far we are from the noisy measurement itself. And the second term, which is the key here, it's the correlation between our estimation and the noise in the image. Okay? Because the rest is going to be a constant that doesn't depend on F, so we don't really care when we're optimizing F in the neural network. Okay? And the key term will be to try to get rid of this in a way that we only end up with the measurement consistency term which we can compute easily, right? We just need Y. Okay, how can we do that? The first approach for doing that is to say, okay, maybe we can observe two independent noise realization of the same image. So I'll write here as YA, so that will be one noise realization of the image, and YB, another noise realization of the image. But here, importantly, they share the same X, so they share the same underlying image. And the noises have zero mean, which is generally the case. Okay. In this case, this famous term here that we want to approximate is 0 if we input one image to the neural network and we use the other as a target. Why it's 0? Because the expectation goes due to independence. We can factor it in the first term and in the second one, and we end up that the second one, because we have zero mean noise, it's 0, right? And so training on two noisy copies of the same image, where we put the first copy at the input of the network and the second as a target, is enough to obtain a supervised objective in expectation. This looks a bit magical at the first time you come across, because you're going from noise to noise. So the method is called noise to noise. But because you cannot overfit the noise in the target, because it's independent from the one in the input, the neural network does the same as in the supervised case. And this, here I'm writing it for additive noise, but the idea extends very well to any noise distribution that has 0, so whose mean is the image, so it has 0 mean. Okay, so like Poisson, Gaussian, etc. There is one big limitation of this method, is that in practice, if you have a machine, you generally observe one object just once. You don't observe 2 times the same object with different noise copies, right? And so this is quite limited to specific setups where we observe these 2 noisy copies, all right? So what can we do if now we observe just one image per one noisy copy per image, okay, which is the normal setup? So if the noise is Gaussian here, we can do a little trick which looks quite magical as well at first when I heard about it. Is we can create these 2 independent noisy copies by adding more noise. So basically we have YA, we created by taking our noisy image Y and adding more noise times an alpha, that it's a constant that we can choose arbitrarily, and YB, which is removing that same noise. And it's very easy to show that these 2 variables, YA and YB, are now conditionally independent on X. And so because they are independent, we can use the exact same result as before. So this is, I suggest you prove it yourselves, but it's like a one-line proof. And we end up with a loss here, where we are adding this additional noise omega, which looks exactly the same as noise to noise, but just comes with one specific Y. So there is a price to pay here, is that because we add a bit of extra noise to our Y to obtain YA and YB, the SNR of the input of the neural network will be smaller than the SNR that we have at Y, so the signal to noise ratio. And at test time, we'll need to do multiple evaluations, because we are adding noise, so we can add it multiple times and average over all those noise realizations. And the other thing we need here that is kind of hidden is we need to know the noise distribution, because the added noise omega has to have the same variance as the noise affecting the measurements. Otherwise, this proposition doesn't work. Okay. But this result is I find it very elegant, and tomorrow in more extended talks we'll present some extensions of this idea beyond Gaussian noise to any exponential family noise distribution. And we'll see that this can be done to Poisson, gamma noise, all the types of noises that you encounter in practice. All right. Another way of dealing with just one noisy copy is via Stein's lemma. So Stein's lemma tells us that this famous cross term that we need to approximate, so the correlation between the noise and our prediction, in the case of Gaussian noise, is given by this very simple expression, which is the divergence, so the sum of the derivatives of the neural network times the variance of the noise. Okay? And the nice thing about this is that we, on the right, we don't need x. There's no x whatsoever, so we don't need ground truth. Okay, so this is a result from 60s and still holds very useful today. And so just replacing this term, the cross term, by its equivalent in the divergence, we end up with what is called the Schur loss, which basically, again, we have two terms. The first one will enforce measurement consistency, that we're not too far from the actual noisy image. And the second one is that we don't want the denoiser to have a large divergence. So intuitively, what does that mean? That a good denoiser should not be very wobbly, because if it's very wobbly, it can overfit very easily the noise. So if we penalize the divergence of the derivatives of the denoiser, it will not be able to overfit as much. And given using Stein's lemma, we know that this is also an unsupervised estimator of the supervised loss. So this should give us as good as supervised learning. We can extend this to other noise distribution, like Poisson noise, and tomorrow I'll also be speaking a little bit more about that. Using Hudson lemma, which basically is replacing this divergence by some variant of this divergence according to the noise distribution. But something important here is that we still need to know the variance, right? So we need to know the distribution and the variance, because otherwise we cannot compute this term that is multiplied by sigma squared. We can do this trick even beyond the exponential family for Poisson Gaussian noise. There's multiple research works on the topic. So how can we compute this divergence in practice? We could use PyTorch and AutoGrad to compute gradients automatically, but what is mostly done in practice is to approximate this divergence with a Monte Carlo estimate, which basically consists in adding more noise to the input. Okay, so it kind of sounds like the previous one I just spoke about. And doing this finite difference to estimate a derivative. Okay, and we know that in expectation this thing is the same as the divergence. And the other thing we kind of can guess from looking at this formula is that this looks a little bit like the noisier to noise. So we add more noise to create an independent copy, right? It looks a lot like that. And tomorrow, more in depth, we'll see that there's actually some equivalence between this approximation and the noisier to noise approximation. All right. So one nice result about Schur is that it gives us the very popular nowadays Tweedie's formula. And what do I mean by that? So if we want to optimize this term here, so the Schur loss, we can see that this is an expectation with respect to the probability of y, right? So here you can imagine an integral over p of y. And to simplify this derivative that it's annoying me, I can just do integration by parts. And when you do integration by parts, you generally take the derivative of the other term and remove the derivative of one term. So if you do the math more in detail here, I went a bit fast, you will find that we'll give you this thing where we see p of y, distribution of y appearing. And now I just need to complete squares. So this is a quadratic formula with respect to f. And when I complete the squares, I see that actually this Schur loss, if we look for any denoiser function f, it has a very nice analytical formula, which is say that the optimal denoiser here should be just y plus sigma squared times the gradient of the log probability of y, which is often called the score of the distribution. And this is, again, the MMSE estimator. So this is the expectation of x given y. And you might have seen this formula appearing in diffusion models, because this is what's used to do sampling in diffusion models, to do some kind of gradient descent over P of y with this formula here. But in the setup of self-supervised learning, we can use this formula. Actually, we can look at this and say, well, we'll see that denoising is self-supervised. We don't need P of x, we just need P of y. P of y is a distribution of the noisy data, not distribution of the clean data. So just with P of y, we can get around and get our optimal denoiser. And so there is this method called noise to score, where the idea is to learn this score function from the noisy data and then apply this formula to do the denoising. Okay. And we'll come a bit back later, but as I said, this is the key formula and diffusion model. So to summarize so far what we have seen, the first approach is noise to noise, where we have two copies of the same per image, okay? And this gives us something that is going to be MMSE optimal for one of the copies. And it can work for any noise that it's zero mean, okay? So we don't need to know the noise if we have the two copies. In a way, having the two copies is kind of having knowledge of the noise, Then we saw that if we don't have these two copies, we can create them as long as we know the distribution of the noise, which is the noisier to noise approach. And we saw that there's also a similar but slightly different approach, which is Stein's unbiased risk estimator, which, if we know that the distribution is Gaussian or a specific exponential family, we can construct also a loss by penalizing the divergence into something that is MMSE optimal. So all of these are very close to the supervised case, because in every case I said we can get something that is as good as supervised, but all of them require knowledge, where require either two copies of per image or knowledge of the noise distribution. And you can ask, okay, what if I just have one copy of per image in the distribution, and I don't know the noise distribution because my camera is giving me degraded images and I don't know what they are degraded by. I just don't know if it's Gaussian or whatever. And we'll see in the next that there are some approaches for this. And the first approach is some recent work that, again, we'll be speaking more in depth tomorrow, where the idea is to say, okay, what if the noise distribution is Gaussian, but I don't know the variance, which is a reasonable assumption in many setups, right? So what we can do is to say, we'll minimize this object, this loss here, which is basically just the measurement consistency again, with a subject, so a constraint that the divergence of the expected divergence is zero. This might look a little bit weird at first sight, but if we go back to shore, we'll see that this makes sense. Why? Because if the divergence is zero in expectation, we know that in expectation, this term that we need to use in shore will be zero. And if it's zero, then we don't need sigma square, because we don't need to know this term at all, right? So we get rid of the requirement for the noise distribution. So this will not be optimal. So we will not get the MMSE estimator, the posterior mean, by solving this problem. Why? Because the posterior mean does not verify this constraint in general. And we'll see more tomorrow. But we'll see also tomorrow that this is almost MMSE optimal. But it's kind of safe. And not knowing the noise, the noise level is not valid. It's not a big price to pay. We'll see tomorrow other generalizations. So now, what happens if we don't know anything? We don't know that the distribution is Gaussian. The only thing we want to assume now is that the distribution is separable. Very often the case that the noise affecting every pixel is separable across pixels. So it's an independent noise for each of the pixels. So what we can do is to take an estimator, F, so a denoiser network, that does not use the central pixel to make its prediction of the output pixel. Okay, what do I mean by that? So basically, that the derivative of the ith output with respect to the ith input is exactly 0. And why do we need it? We need that because when we look again at our cross term, and now here I wrote the cross term over the sum of all the pixels, we see that if the noise is separable, we can again show that this is 0 as long as f doesn't use the information about yi for a prediction of the ith output. It's also relatively easy to show. And this looks a bit like cross-validation in the sense that I remove the central pixel when computing the loss at that pixel. And it's kind of a cross-validation. So this in the end looks a bit like this loss over here, where we want to again have measurement consistency, but now we will subject our function to have 0 dependency on the ith input for the ith output. Again, if we look at Shore and we think of the special Gaussian noise case, we'll see that this, if we make every derivative, we force it to be 0, then of course this thing will be 0, and we don't need sigma squared to compute it, right? But now the constraints are much bigger than before, because we are looking for denoisers that have 0 derivatives, so they don't look at the central pixel to make the center prediction, and this is losing a lot of information. So they will be further away from being optimal as in the supervised case. And there are different ways of implementing this in practice, because it's not obvious how to force this derivative to be 0. Let me explain this more in detail. The first way to do this in practice is what's called measurement splitting. So the idea is that if I have now my image, I can divide it in 2 parts, YA and YB at each epoch, okay, at each training iteration, and I will put one split inside the network, and I will ask it to predict the other split. So in that sense, it cannot use the value itself to predict the pixel. And I will change these splits randomly at each training. So this is the idea behind noise to void or noise to self, where, for example, in noise to void, they want to do denoising. So they have patches like this. And so they will give the noisy image to the neural network, and they will flip the value or put it to 0 at the input, and only compute the error at that specific pixel. So the neural network cannot overfit the noise in that pixel. Right. There are more advanced ways of doing this, or more clever, let's say. If we think of an image, it's a grid, and we can separate it into non-overlapping grids by taking down samplings of the image. And we can use one of the grid to go to the other. So we'll input in a neural network one grid, and we will ask it to predict a non-overlapping set of pixels for another grid. Okay, and we will randomize this training. So this is the neighbor to neighbor class. And this works very well in practice if your images are somehow smooth. But it's assuming that the downsample grid is somehow the same distribution as the original grid. So at test time, we have trained our network to predict from one part to the other. What can we do? So we can just test the neural network as we trained. So what do I mean by that? We will evaluate all the possible splits. So we will remove some pixels randomly, take a prediction, and average over all the possible removal of pixels. So in this way, we test the neural network exactly as we trained it. Or we can close our eyes and take a more like a deep learning approach and say, well, it should have probably generalized for this, and we will just take one random split and we will evaluate that. Or we can even say we will put the whole image in it and just hope that it works. And even though here this is being tested differently as training, because training we have given missing pixels, this can work okay in practice. Another way of doing this cross-validation method is to literally build the lack of dependency in the input pixel in the architecture itself. So this is called the blind spot neural network, because it will not look at the center pixel when making its center pixel prediction. And in this paper by Lyon, they show that you can take CNN and work it around with some rotations, avoid using the central pixel for making it. The nice thing about this is that because the neural network has this their zero derivative constraint built into the architecture, just train on the measurement consistency, and that's it. It will work much faster for training. But the price to pay is that you cannot use any architecture. You need to use this very specific architecture. There's one final approach I want to mention. You probably, when you think about doing self-supervised, unsupervised denoising, something intuitive is to say, why not using an autoencoder? Why not putting the image into some neural network that will go into a smaller space and then go back to the original space? And what is the idea of that? Is that if this encoder is reducing the size a lot, the noise will not be able to go through the encoder and back through the decoder, right? And looking it from the perspective of Schur and the perspective we have been taking, this is kind of saying that the divergence of the function should be small, because if it has a strong bottleneck and it has a control Lipschitz constant, its divergence will be small. So again, here, if the divergence is small, we can just train on measurement consistency. And the idea is that the noise distribution is high dimensional. It cannot go through the bottleneck, so it cannot propagate to the output. And to give you a more precise example of this, if we build a linear denoiser with a bottleneck, it means that we are multiplying by a matrix that is low rank, and the divergence will depend on this rank constraint. So to summarize everything I spoke about, we have a family of different methods, and there's different trade-offs. So above all, there is noise to noise, which gives you something that is quite close to, well, that is MMC optimal for the specific inputs, that it works for unknown noise distributions as long as they have zero mean, but requires 2 independent copies, not very practical. We can relax that by having some knowledge of the noise distribution, either with recorrupted to recorrupted, noisier to noise, or Schur. We can relax even further, having knowledge of the exact noise level with unsure and this family of methods, while keeping something that is relatively close to MMSE optimal. Or we can go all the way and say we don't know anything about the noise distribution except that it's separable, and use cross-validation methods or autoencoder. But these methods will generally be quite further away from the supervised case. And a kind of mathematical picture for this that we'll be speaking more about tomorrow in Mike's talk will be that in the left we have perfect knowledge of the noise distribution, and we know that we can be a little supervised. On the right, we have very little knowledge of the noise distribution, and we'll pay a price. And there's also middle ground where we know something about the noise distribution, and we can be half optimal, let's say. So I wanted to end this section with one results, because I've just been speaking about math, and let's look at some images. So this is an experiment where we got some cryo-electron microscopy, as Mike presented, image. Here, I'm not gonna do the full inverse problem of reconstructing the molecule, but just removing noise. So that this will be my goal. As you see, that the images have extremely low signal-to-noise ratio, and we can still do a self-supervised denoising. So training a denoiser network only on these images themselves. Here we know that the noise is approximately Gaussian, Poisson Gaussian, so we will use one of the methods exploiting this information, and we can get something that finds a lot of structures. That actually there was a lot of information buried in the low SNR, and actually there was some kind of molecule information projected here. So you see that you can use all of these methods to actually discover structures present buried in the noise in the data that by plain eye you would not be able to do, and by using an off-the-shelf denoiser you would not that was not trained on these specific these specific features, it might fail or give you hallucinations. So one quick word beyond denoising. As I said at the beginning, if the operator is invertible, we can obtain the same as before. So we will just adapt any of the losses that I presented before to, instead of targeting the supervised error weighted by this matrix A. Okay, for example, in the case of Shure, we can do this by putting a bit everywhere, but you can do it for the noisier to noise. You can do it for other methods as well. And we have two cases. If the operator is invertible, we know that this pseudo-inverse will give the identity, so we will be targeting the supervised case, because if we go back here, this is the identity and the supervised error. Okay. But if it's not invertible, if the operator is not invertible, then we will not be targeting the supervised case because we'll have a null space. But going back to the picture that we saw before in the first part, if for example, we have an in-painting problem, the neural network can do a very good job at removing the noise in the observed pixels. But because it has no information in the null space, so in the mixing pixels, can give whatever prediction, and because we're only going to compute the error in the measurement space after applying A, we'll not be able to learn this part of the distribution. Okay, so we'll see in the next parts of the tutorial what can we do to deal with this missing information from graph and non-invertible operator.